Hello, this is the Chapter 5 lesson. Chapter 5 is about the role of probability in statistics. We're going to break this chapter up into 4 sections, Part A, B, C, and D. Here in Part A, we're going to talk about what is probability and what does it have to do with statistics. Sometimes we miss the connection between probability and statistics. Really, everything that we do in statistics is based on the idea of probability. Starting in Chapter 6, the theoretical foundation for everything that we do is probability. Now, we're not going to get into the deep, dark details of the theory behind all of what we do, but we need to at least be familiar with some of the basic ideas and the basic terminology of probability. And so that's the goal here of Chapter 5. So first, let's talk about what is probability. Now, probability, we're not going to give a formal mathematical definition of probability. And in fact, defining probability mathematically is actually very complicated. We're just going to take a very conceptual idea. So probability, we'll take it as a measure of how likely something is to happen. And probabilities take values between 1 and 0. Probability of 0 means that something is impossible. Probability of 1 means that it's absolutely certain to occur. Probability of 0.5 means there's a 50-50 chance. If the probability is close to 1, then we say that it's likely. If the probability is close to 0, then we say it's unlikely. Okay? So probability, or at least that term, word probability, is something that we use in normal everyday language. But one question that we might ask is, well, just what exactly does probability have to do with statistics? Well, to start to answer that question, let's review a couple of definitions that we've seen before, namely population and sample. Population is the collection of all individuals about whom we want to make a generalization, and then the sample is a subset of individuals from the population. And as we've mentioned before, the difference between the population and the sample is what statistics is really all about. We want to know something about the population, but in order to know that, we'd have to go out and get information from every member of that population. That's virtually impossible to do. So instead, we go out and we get information from a sample, which is relatively easy to do, and then we're going to use that information to make generalizations about the population. And probability forms the foundation for how we make those generalizations. Okay? So a couple other definitions that we need to remind ourselves of are a parameter and a statistic. Parameter is a number calculated using information from each member of the population. So for instance, a population mean that will denote mu is an example of a parameter. Now here in a bit we'll give a more precise example of what this means. But if we went out, we got information from every single member of the population and then calculated a mean, that number we would denote mu. We'd call that the population mean, and that's an example of a parameter. Okay? And so then a statistics is a number calculated using information from each member of a sample. So if I go out and get information from a sample and then calculate like a mean, we would call that mean x bar. We'd call it a sample mean, and that's an example of a statistic. And so when we get information from a sample, we calculate statistics. We really want to know parameters, so we use these information from the statistics to make conclusions or generalizations about the values of the parameters. And probability forms the theoretical foundation for how we make those generalizations. Okay. Another set of definitions that we've talked about before are descriptive statistics versus inferential statistics. Back in chapter 4, we talked about descriptive statistics, which summarize a sample selected from a population. So descriptive statistics would include things like graphs and calculating sample means, those types of things. Inferential statistics are where we make inferences about population parameters based on sample statistics. So again, inferential statistics is all about this idea of using information from a sample to make a generalization or conclusion or inference about a population. Statistics forms the theoretical foundation for how we make that inference or that generalization. Okay. This simple diagram here illustrates those ideas. So we've got a large population that maybe we want to know the mean of that population. But in order to determine that value exactly, I'd have to go out and get information from every single member of this population. And that's very difficult, if not impossible, to do. So instead, I go out and I look at a subcollection of members from that population, call that a sample. We collect data from every member of that samples, and we get n, which is our sample size, and x bar, which is like a sample mean. Those are examples of those are statistics, and then we're going to use that information to make generalizations about this population. So when you calculate like a sample mean, that's an example of a descriptive statistic. When we use that information to make generalizations about the population, that's what we call statistical inference. Okay. So to illustrate this idea, let's look at this example. Suppose we want to know the mean weight of all adult males in the United States. So in order to calculate that number exactly, I'd have to go out and weigh every single adult male in the United States. I'd have to add up all those weights and then divide by the total number of males in the United States. If we were to do that, we would denote that number mu. We'd call that the population mean, and that's an example of a parameter. But doing this is impossible. I can't go out and weigh every single male in the United States. So knowing the exact value of mu is impossible. Okay. So suppose that we go out and instead of weighing every male in this population, we weigh each male in a sample of 500. Now that's relatively easy to do. And then we calculate x bar, our sample mean, which is the sum of the weights from all males in that sample, and then divide by the total number of males in the sample, which is just 500. Now, that's numbers relatively easy to calculate, again, because weighing 500 males isn't terribly complicated. And let's suppose that we did that, and we calculate a sample mean of 180 pounds. So we went out, we weighed 500 guys, added up their weights, divided by 500, and we got this average of 180 pounds. Now, our hope is that this sample mean of 180 is a good estimate of our population mean mu. That's when we calculate sample statistics, we hope that they're good estimates of the population parameters that we're really interested in. Okay. So a couple of questions that we might ask related to these parameters and these sample statistics are, number one, how likely is it that mu is close to 180? Or in other words, what's the probability that mu is close to 180? That's an idea that we're going to answer more formally starting in the next chapter. Okay. And then in later chapters, we're going to be talking about claims. And so suppose that we claim that mu is equal to 200. Now, why would we do that? Where would that number come from? Well, don't worry about this right now. We'll talk more about that later. But let's just suppose that we claim that the true value of mu is 200. Now, assuming this claim is true, how likely is it that we get a sample mean of x bar equals 180? So we actually went out and we observed a sample mean of 180. If our claim were true, just how likely is this to occur? Well, probability is going to give us a way of answering that question. And then based off of that answer, we might ask, what does this say about the validity of our claim? Well, if this number here is very unlikely to observe based off of this assumption, then that's maybe an indication that our assumption is incorrect. And so that idea kind of forms the idea of what we're going to be doing later on in the semester in what we call hypothesis testing. So the basic idea here is that we're going to be able to use probability to analyze results from a sample to try to make some conclusions about a population. That's why probability is important. So to start off with, let's look at a real simple example of calculating probabilities. So let's take a population here of children, and we've got a total of 5,290 children in this population. Let's suppose that 2,560 of them are boys and 2,730 of them are girls. And then for each one of these children, we record their age. So we've got 840 of them are age 5, 892 are age 6, so on and so forth. This number right here says that 435 boys are age 5. This number, for instance, says that 412 girls are age 7, and so on and so forth. So let's suppose that we randomly select a child from this population. So what that means is that each child has the same probability or same likelihood of being selected. So to calculate the probability that this child has some characteristic, we'll talk. A characteristic is a very generic term, meaning just something that distinguishes this child from other children. So probability that that child has a characteristic is the number of persons with the characteristic divided by the total number of persons in the population. And that total number is denoted n. In this case, n is 5,290. Okay. So suppose let's look at a couple of examples of calculating probabilities. Let's calculate the probability that we get a boy. So by our definition is we're going to take the total number of boys in our population, 2,560, divide it by the size of our population, 5,290. We do that arithmetic and we get 0.484. Now let's look at another example. Suppose we want to calculate the probability of selecting a child that is at least 8 years of age. And so that means the child is either 8, 9, or 10. So what we need to do is calculate the total number of children that are at least 8 years of age and divide it by our population size. So we have 846 that are age 8, 881 that are age 9, 918 that are age 10. We add those together. That's the total number of children with our characteristic. We divide that by my population size, 5,290, and that gives us 0.5. So there's a 50-50 chance of getting someone who is at least 8 years of age. So there's a couple of very simple examples of calculating probabilities. In part B of this lesson, we're going to look at calculating a little more complicated probabilities that we call conditional probabilities.